So a buffer is a solution that can resist pH changes. Why is this important? Where are there buffers in your body? Yes. In the blood. Perfect. In my blood. Okay? There's a couple different buffer systems going on. A hydrogen phosphate-based buffer system, and we have bicarbonate. And these are things in your blood that are going to be preventing any extreme changes that are dangerous. I'll probably use I already know what problem I'm going to put on the next homework related to this. It's a totally valid problem. It has real numbers in it. It is somebody has extreme alkalosis. Their blood is really, really alkaline. They have a really high pH that is unhealthy. And if I deliver a bolus of acid to their blood, just like inject it, which is a totally real thing that they do, did I give enough to bring it back down to the healthy, regular level of 7.4? Or, I could change it. How much do I have to give to bring it down to the right amount? But yes, in the blood, okay? So to set up a buffer, I need a weak acid because I need to be able to have this piece here. I need to be able to have the acid in my solution and have it not dissociate, okay? Or dissociate very little. So I can have the acid hanging around. So when I make a buffer, I'm going to mix a weak acid with a conjugate base for that acid. So acetic acid would be usable, okay? Acetic acid, CH3COOH, is a weak acid with a pKa of about 4.76. And this is for 25C or room temp in H2O, okay? So your pKa might vary depending on temperature and what the solution is. This information would be given to you. Okay. And pH would be equal to about 2.88. And this ratio would be about 1.31 times 10 to the negative second, or about 1.3% dissociation. All of this information is sort of confirmed and explained in more detail in section 1015, if you want to read that. The other thing it does is it talks about pH of water and like how to set up pH of water being 7. I'm not going to ask you any stuff about that, okay? But if you're interested, I want to ask questions about 1015, but if you want to know. So the conjugate base of my acetic acid is CH3COO minus, or my acetate ion. Okay. And so in order to get acetate ions in solution, I can put in usually I'm going to do some sort of salt of my conjugate base. In this case, it could be sodium. Sodium acetate, or like I said, just some salt plus conjugate base for whatever I'm trying to make my buffer out of. And so then I have NaCH3COO going to just sodium ions sort of together, and then when I put it in water, it dissociates completely into sodium ions and my conjugate base. So then, if I mix together equal molar amounts of my acetic acid and my sodium acetate, this is my concentration of my HA and my sodium acetate, which is my Na plus, and then my conjugate base. Mix equal amounts in water. I can make myself a buffer. This is not going to dissociate appreciably. This is going to dissociate completely. And so I'm going to set up this relationship here. And then I will know that I've made a buffer where my pH is approximately the pKa of acetic acid. So let's say we mix together 5 millimolar each. Okay. So I've set up a buffer where I have put together 5 millimolar each of acetic acid and sodium acetate in water, and my pH starts at about 4.76. And then what I'm going to do is add 1 millimolar of hydrochloric acid to the solution, to my 5 millimolar each of weak acid and salt. Okay. HCl will dissociate completely. It's a strong acid. I expect it to completely dissociate, so I go ahead and assume that 1 millimolar HCl gives me 1 millimolar of protons. I assume it just dissociates completely. It's very strong. So 1 millimolar of HCl being added is essentially 1 millimolar of protons once it gets in the water. And what the protons will do is they'll join up with the acetate conjugate base and put back together acetic acid. So HCl will go in, it'll dissociate, and these protons will grab the base and become acetic acid. So I'm interested in what happens to pH when I put this HCl in. I have pKa. That's really not changing. That's the pKa of acetic acid. And then I have log base 10 here of, on the top, I have my conjugate base, but I'm losing some of it. When these ions go in, they grab up the base. So the concentration of base decreases by how much protons I put in. On the top, on the bottom, I have the amount of acetic acid that I started with. And essentially, when these two things combine, I'm getting more acetic acid out, so I'm increasing the concentration of acetic acid based on the amount of protons I put in. Okay. So these are both 5 millimolar. This was 1 millimolar. Okay. If you plug all this in, this was 4.76. You can plug in log base 10 of 4 millimolar on the top, 6 millimolar on the bottom. The inside term here is 0.67. So I get a final pH of 4.58, which is not a very big difference from what I started with. And I've essentially buffered this pH change. If I put 1 millimolar of HCl directly into water, I expect the pH to be 3, not 4.58. Okay? And so I have prevented this really steep decline in pH.